Hello, everyone. Okay. So thank you for staying back. And also thanks to the organizers, especially Vinod, to have invited me. And I'm very happy to be back to Alma Mater. And it's a nice experience to be on the other side. So I'll be giving a journey today of different estimators of conditional mutual information, what has been there in the literature, and go all the way towards deep learning based estimators. So that will be the talk today. In the interest of time, I'll delegate the proofs to another successive refined version of this talk, which may be elsewhere. But I'll be happy to take questions offline if there is interest. This is a joint work with Sudipto and Sriram at UW. Now, okay, which means I have to be here. So many of the speakers throughout this bits have talked about biases, and I heard there was a session also yesterday around this area. So let me pick on the same topic. We have a huge data, and every data point has many fields. Some of those fields can be of very large dimensions. So we have, say, education, gender, salary, and performance. Performance can be very high dimensions. And I'm interested to understand, is, say, gender independent of salary given performance and performance evaluation and education, right? So you can already see throughout the bits here that this notion of conditional independence is important in detecting biases, right? Also in this emerging new area of fair AI, AI for fairness. Then for those who are aware of causal inference, the first engine before many of the algorithms which detect causal directions, first you check for conditional independence, right? And then there's feature selection, inference and time series, so on and so forth. The problem is simple. You have X, Y, Z, 3 random variables. You have data given in the form of samples and coming from an underlying distribution, and you want to check whether X is conditionally independent or not of Y given Z. Now here I can fork off in a direction of hypothesis testing, right? I can take null hypothesis to be conditionally independent, accept or reject it. I will not do that here, but rather I'll be interested in plain and vanilla estimation of conditional mutual information, because that can also act as a proxy. You know, it may not give p-value control conditional independence test, but you can threshold it around 0 and give your hypothesis test as well. And in and of itself, this is a useful quantity, which we see in feature selection and causal inference, so on and so forth. And particularly for me, it's interesting because I spent my 5 years in Stanford coming up with rate regions, which in the end were not computable. And then we just plot a simple graph on binary data and showed that, okay, we get some rate regions. But here, what if we can give some nice estimator about these important information quantities? Okay, so let me first take a detour and dwell more on some other thoughts about these information measures, especially mutual information and conditional mutual information. So if Z is null, this is mutual information. And it is computed as Kullback-Leibler distance between the joint Pxy and the conditionally independent joint, which is Px and Py, right? So expectation taken over the joint of log of the ratio, right? Ratio of these two distributions. And the distance indicates a measure of dependence. If the distance is much, which means mutual information is much, that would mean the distributions are different. So there is some dependence, okay? And these measures kind of tell a bit more, both mutual information and conditional mutual information. They extract out the nonlinear dependence, which other measures like Pearson coefficient are not able to. So these two examples show that there is a dependence, Pearson coefficient vanishes, but we have some sort of capturing ability from mutual information. Okay. So same can be said about conditional mutual information. It is written as a divergence estimation or divergence calculation between the joint Pxyz and the conditional independent joint, where there's a Markov chain from X to Z to Y. Okay? And again, this is the nice equation on which I'm, even kind of foreseeing my hypothesis test also, which is not a p-value control test, but it is, some sort of test. However, in this talk, we'll just estimate CMI. Another interesting property of CMI, which emerges, is that more than mutual information, which is just the relation between two variables, here there is a relation between three variables, so I can rule out certain directions when there is an underlying directed graph. So if conditional mutual information is 0, I can rule out immoralities, what they call in the causal inference area, or fork, collider. This is the fork and the other is a direct chain. So at least I can rule out this. So there is some sense of directionality involved also when we are talking about CMI. Okay. So back to the original problem, we have n samples, and I have to estimate conditional mutual information. So let's see the prior art in this area. Well, the most vanilla basic way of doing it is plug-in estimator. I will estimate joint distribution, p hat xyz. I'll estimate the conditionally independent distribution, p hat xz and p hat yz, all right? And then I'll just plug in expectation, or which is summation here, empirical sum of log of the ratio of both of them. So this is our plug-in estimator. And we can already see that this is sample inefficient, you're doing too much, it's overkill, and it breaks down when especially things are high dimensions. And here we are talking about, you can remember the previous example, X was gender, Y was salary, and performance, which is Z, can be huge. Nowadays, people are evaluated in corporate and academia on a lot of fields. So that can be a huge variable, a huge number of dimensions, okay? So then we move to another sort of class of estimators, which I like to bucket them as sigma H estimators. So what you do, you write this information or any other information measure as appropriate algebraic sum of some entropies. So throughout this talk, I'll be focusing only on continuous probability distribution, so I'm using differential entropy, okay? But these can be routinely, with some lot of algebra and measure theory, taken towards mixed distributions also, where you have both mixture of discrete and continuous. But anyway, here conditional mutual information can be written as this sum, and instead of doing the plug-in, here I'll be interested in just estimating these quantities, that's all. The differential entropy of x and z, differential entropy of yz, z and xyz separately. A whole lot of work has been done in this direction. And perhaps the best of those comes from a very different area. I think it was perhaps physics or something. And this is the nearest neighbor way of estimating these entropies. This is also called the KL estimator. And I'll just pictorially represent this without going into the detail. You have a lot of samples. For every sample, you query a distance which has k nearest neighbors, estimate a proxy of density around that point, use that density along with some bias, and come up with an estimator for entropy. Do the algebra. Here you have a KL estimator of conditional mutual information, mutual information also. And in one of our recent work, we showed it can be for any information measure. Now, this is a kind of decoupled way of estimating. You're estimating separately hxz, then hz, then hyz in their different spaces. So can we couple them up? And this was again from physics, Kraskov, Stroberger, Grassberger in 2004, which came up with this coupled estimator. And until recently, it was not shown to be consistent. Only 2017, a bunch of information theorists got together and they demystified the KNN nearest neighbor method estimators. Okay? Again, let me indicate it pictorially here. So I'm just considering two variables x and y. So you have a point xi and yi. I'll again query for a distance such that in that ball, again I'm not going what is the metric here, in that ball you have k neighbors. Now I could have stopped there, estimated f hat xy and then gone to x space and y space, but in this KSG method I project those nearest neighbors on the x space and the y space and kind of jointly use them in estimating my metric. So I'll just speak that much about it. And note that the quantity which is being summed is a proxy for log of Radon-Nikodyn derivative, which is here the ratio of the joint and the conditionally independent joint. And we know that this will converge to, and it indeed converges to, mutual information. So like that, I can give a KSG version of estimating conditional mutual information. But the problem is of cursive dimensionality here, and routinely these methods break down. And for a very simple example, even if x and y are one dimensional and z is huge. So let's take an example here where the data actually lies in a low dimensional manifold. So x is a standard Gaussian, z is a huge dimension variable, right? But y only depends on x and z through the first dimension of z only, that's it. So if we applied the entire KSG machinery on it, it is searching around in the entire space of, say, 20 dimensions, but actually it's a low dimensional manifold. So it will get fooled and it just breaks down. This is just one example to show that we need to go further, and this talk is towards going that last mile, further mile, about new estimators of conditional mutual information, thinking in a very different way. Beyond plugin, beyond algebraic sum, and also beyond this coupled KSG estimator. Okay? So let's write the CMI again as a Kulvik-Leiber divergence between joint and conditionally independent joint. One way of estimating would be, already I have data distributed as P, X, Y, Z. So if I can generate a proxy for data, you generated using conditionally independent way. So that's why I call it P hat YZ. This P hat YZ is close to P YZ. I have bootstrapped from the given data and generated that. And I come up with a new way of estimating the divergence. Not plug-in way, not the, here I can't do the algebraic way anyway. So this brings us to a modular approach. And it should work well in high dimensions. That's the, something in behind. So it's a modular architecture. And let me explain it pictorially. You have a data, you push aside one set of the data, call it dgen, and use it to train a generator. So which means a map from z to y, which will proxy for p hat y given z. Okay? Then you take another part of the data and you transform it, digest it through this system. So for every point in this other data which is kept aside, you take every point here, you apply the same generator to it, and you will get some yi prime. It won't be exact. And that yi prime is pushed into this in this taken sample, okay? So you can observe that now the new data, the transform data, will be distributed as pxz and p hat y given c, okay? So what I did, I took one part of the data, trained the generator. I took another part of the data, transformed it, and made it into a marginalized or conditionalized distribution, and we have the samples. Now I put it through a divergence estimator, and this will give me conditional mutual information. So which means I have to design two blocks, right? One is the generator block and a divergence estimator block. So let's look at the generator block. Here the vanilla permutation will not work because we have x, y, and z. If I had only x and y, I could keep x as it is, shuffle y, and I will get data generated as px and py. If I do that with x, y, z, I just decouple them all together. It will be pxz and py. So permutation will not help. What will help? And that we want to do good in high dimensions is our deep learning methods. So conditional GANs. Again, this is a whole area of research. I'll just give a, like a 10-second understanding about it. And you can skip the conditional part here. Conditional part just means that Z are given to both of these neural networks. The generator neural network takes a spherical Gaussian noise, which is independent, transform it through its many layers, and produces a fake Y. Discriminator takes that fake Y, which is produced here, with the real Y which it has, to tell how fake you were. And the whole training jointly, and actually it is in steps, to come up with a discriminator which will be around 0.5. That means in the end, if you sample from here, you'll get a good proxy for py given z. So you can actually sample from a distribution which is close to py given z, and let me call it p hat y given z. So this is one way of generating that data. So what was happening in GANs, you took a low-dimensional spherical noise and converted to a data space. In autoencoders such as these, you do the reverse. You take a huge data space, find a nice signature about the data. So that can be, say, a mean and variance, Gaussify it, again pass it through a decoder, and you get y prime, and the whole objective is to reduce some loss between y and y prime. In the end, what you get, if you sample from the output of the decoder, you will get a good sort of proxy for conditional joint, right? Py given z. Make sense? And finally, we have our vanilla nearest neighbor method. Here is one nearest neighbor. You take x, y, z, take z, find the one nearest neighbor, and take the corresponding y and push it back. So this is also helping us to generate the conditional independent distribution. So we have one part of the generation solved. What about the other part? In the context of mutual information, some work has been done in this direction, which is to have a new divergence estimator which can work with high dimensions, which means if we can have deep learning based estimation. So this is the Donsker-Verdhan variational representation. It is SOAP over a bunch of functions and this big loss. We also have an F divergence version of it, which is not so tight, but nonetheless, the forms look enough familiar for a person familiar with machine learning to just train it. So that's what they did. You optimize this F over a nice parameterized neural net, and you get a good divergence estimator. If you put P to be Pxy, Q to be Pxpy, this will give you an estimator for mutual information. So looks like we can just put that, right? We have generator here, which is conditional GAN, autoencoder or nearest neighbor method, and just put mine here. So this is what they call it, mutual information neural estimation by Belghazi, which I showed in the previous slide. And we should get some estimator for conditional mutual information. But that breaks down and is by the problem which Varun also described in his talk, especially because of that weird log of expectation, when you take gradients, in the denominator you have a batch mean and not the population mean. So there are biases. This will give bias gradients, and there are a lot of studies now showing that mine breaks down. So we had to trace back. And here are some experiments also showing that they don't converge and it's unstable. So now the problem becomes, maybe I have to rethink about divergence estimation, right? Instead of taking this whole loss function and optimizing over neural network, maybe something else. And this came through a simple observation. If you look at this expression, stare it enough, then we'll notice that the optimal f star is actually log of p by q. That's a simple exercise, right? So which means that instead of going through this exercise of optimizing over f and worrying about bias gradients, maybe I should do something to get a proxy for p by q. Okay, I'm taking little abusive notation here. Actually, it is x, y, z, but it would be too much, so I'm just subsuming them in x. But x, you can think about huge dimensions depending on what problem I'm addressing. If it is mutual information, x is xy. If it's conditional mutual information, it's xyz. So I can just get a proxy for this p by q and then plug into this expression, and I'll get an estimator, a divergence estimator, and hence an expression for both mutual information and conditional mutual information. Okay? And some of you can already guess where I'm going. Here comes the classifier, already celebrated in the previous talk. Because what can classifier do? Well, say I have a two-dimensional data set. So I will first pre-label them. I'll take the data distributed as P, which is your total joint. It can be PXYZ or PXY. Here I'm just taking some X1, X2. You can abstract out as you wish. And I label the data distributed as P as 1 and label the data distributed as Q as 0. Train a classifier, okay? And you would notice that the likelihood ratio is actually P by Q if it is optimal and trained well. Okay, so any questions? Okay, so what should I do? I just plug it in. And here I get a new divergence estimator. So instead of mine now, I can use this new divergence estimator, which I call it Classifier MI, and we can already contrast these two. What was happening in mine, you were taking this humongous expression, going back propagating it through a neural network and running into all the issues about bias gradients. Here I don't do that, because classifier science in deep learning is much more advanced and mature. So I can have very nice classifiers which approximate, or sometimes this is also called accuracy, but I'm avoiding using it because there can be many notions of accuracy. So this likelihood ratio can be approximated by a classifier, and I just take a log of it and plug it in. So and anyway, this performs much better than mine. Just an illustrative example to compare for a simple scenario of correlated Gaussians. We have plotted the different curves, and classifier MI performs good. But nonetheless, we have a new now recipe for CMI estimator. You do the generation in the first step, and the second step, you use classifier MI to do the divergence estimation. Okay? And this classifier MI is nicely consistent. It has theoretical guarantees, which I will not go into detail. Okay, I have 5 minutes? Yeah, 4 minutes, okay. So what do we have now? We have now this buffet of estimators. The best from the tradition, so tradition, modern, postmodern, you may call it that way. So KSG, way of doing it. Then we have this modular approach in which you do generation and then you do divergence estimation. And in the divergence estimation, I will not use mine, I will use classifier MI. So I can have conditional variational autoencoder and classifier MI, I can have CGAN and classifier MI, or I can have nearest neighbor method and classifier MI. Okay? So we can end there, but serendipitously we bumped on something else. Can we skip the generation step? Because those who have worked with GANs or those who advise students working with the GANs, this is a dragon. It's very hard to train the generative models. And it is training too many deep neural network things separately. You first do the generation and then do the classifier. So can we skip that step? And you will be surprised at the simplicity of the thought which Providence revealed. And that is IXYZ is IXYZ minus IXZ. So no marks for guessing that. But it simplifies the things. How? Now we have a different sort of architecture to estimate conditional mutual information. You take the original data, marginalize it, that will generate a data with only X and Z. Basically you 3 of Y, okay? Now you take dxyz and shuffle it and generate, so you kept X constant or you kept YZ constant, you shuffled X. So you have delinked X with YZ. So you have a d tilde xyz which is distributed as px and pyz. Similarly, you took this data which was distributed as pxz, shuffled it, and it generated a data distributed as px, pz. So now we can plug in our divergence estimator, right? Which is our classifier MI, and have a proxy for I hat xyz, I hat xz, subtract it, and we get conditional mutual information. Here, no generation is involved. Since classifier MI is consistent by difference and simple math, even this estimator, whole estimator is consistent. There was a problem in generative models. For generative models, I don't know anything. It's a very, very in its early stages, I would say. So we have another recipe. The earlier recipe was the modular architecture in which first generation and then classifier MI. And now this new recipe in which you do 2 blocks of divergence estimator, just subtract them. So MI diff plus mine if you want to use the older mine, or MI diff plus classifier MI, okay? And this is where I connect my talk title. This is what I call CCMI, Classifier-based Conditional Mutual Information, which has no generation. You take the data, marginalize it, shuffle it, have 2 blocks of divergence estimator, subtract it. Okay? So this brings me to the end of the talk. We ran several experiments and routinely found this CCMI performing really the state of the art. And what I skipped here, so these are different graphs, maybe you can peruse through in the paper. What I skipped here was better conditional independence testing, and here I mean that we compared some conditionally independence testing sort of ideas where you had hypothesis testing, along with this simple notion of thresholding near 0. And there also we had a good sort of gain, but I'll skip that for time being. What are the future directions? And I think this can bring a new area where we can have really theoretically sound deep learning based property testing or estimating information measures. The next thing which I'm looking at is directed information. And I think Vincent told me that it's easy. So directed information can be one extension. Another is interventional distribution. So we saw from Devrat's talk that we may not need counterfactuals of the Pearl's causal inference. We may treat what data is obtained as a factual and argue what if it was not there. So you don't need an external intervention, but just from observation you deduce something. So here also we are thinking that can we proxy interventional distribution using such deep learning methods, and this has been a recent interest. Okay, thank you very much.
For one or two quick questions.
Yeah, Lalita.
It's not clear whether I'm making sense, but there's got to be some sample complexity cost for you to estimate those distributions. You go back to the slides.
For the generation or for the classifier?
So your last method.
Yeah, but that was good because it's only classifier, and I can still do that. But for the first, the methods which were modular, I don't know, generative models, it's and it's been a while also. I haven't kept track of what's going on. Which one?
Go back a few more slides.
Okay. Yes, this one.
No, go back. Yeah, so here, wouldn't there be a cost to doing this marginalizing? I mean, I somehow have to parse my data. There's this whole complexity cost of the distribution.
Oh, which complexity are you talking about? If the complexity to marginalize it, but I can just throw away y, right? So, okay, thank you.
Okay, maybe we can take other